This video is going to begin the process of talking about forces quantitatively. There's already been a number of videos that went through how we draw free body diagrams and think about forces and accelerations in a qualitative conceptual way, and now we're moving on into doing calculations. So some of this might feel like review because we are returning to the same ideas, but if any of this has completely lost you, you probably want to go back and watch some earlier videos. So this is going to focus on equilibrium, which is section 6.1 of NITE. And the goals for this video are going to include defining the equilibrium model, which we have talked a little bit about already. We're going to apply Newton's second law to objects in equilibrium. And we're going to begin calculating forces in 2 dimensions. And again, after this, after equilibrium, we'll move into a non-equilibrium situation where we will continue to apply Newton's second law and do some calculations. Now, I do want to highlight that these videos are meant to be more introductory lectures, so I will do some examples, but I'm not doing some very long calculations. For those of you in Physics 202, you should be looking at the problem-solving videos for some extended examples of how to do these calculations. So there are 2 big student learning outcomes that this connects with. First is the idea of representation. We are still drawing free body diagrams, and that's still very important, and especially for equilibrium models. So anytime that we're working with free body diagrams, you should be thinking about representation, and that free body diagrams are where the physics happens. Now, the second thing is problem solving. We are now getting into setting up some calculations, and again, that's based on the free body diagram, so they both come in here. So first is just what is equilibrium? And again, this might feel like a review because this was also covered in Chapter 5, Section 6, but in that case, we weren't starting to do calculations with forces yet. So there's 2 types of equilibrium. First is an object at rest, that stays at rest. And the idea of equilibrium is that our motion is constant, that we don't have any change in velocity, which is the same statement as saying that we have no acceleration. Now, one thing that I want to highlight here is this should be a vector, and so this change in velocity should be change in velocity vector. Since remember, you can have a constant speed but a changing direction, and in that case there is an acceleration. So that's really important to remember. So equilibrium is motion being constant. That's either an object at rest staying at rest, or an object in motion that is traveling at a constant speed in a straight line. So either of these are equilibrium. This one's at rest, staying at rest, constant, uniform motion. So in both of these cases, acceleration is 0. And based on that, we know that F net is equal to 0. How do we know that F net is equal to 0 if acceleration is equal to 0? That's coming from Newton's second law. We can say that Newton's second law has 2 forms. Just rearranged, F net equals mass times acceleration, or acceleration equals F net divided by mass. Same equation, just rearranged. And so if we know that acceleration is equal to 0, F net must also equal 0. Just a brief note to remind you on notation, net means total, and this big sigma symbol is also just a summation symbol. So this means add up all of the force vectors. So these are 2 different ways of expressing the same mathematical idea, which is that you take all of your forces and you do a vector sum. So from Newton's second law, if acceleration is equal to 0, the only way we can have that is if net force is equal to 0. So equilibrium is the statement that both of these things, acceleration, which was our change in velocity, and net force is 0. So what else can we do? We now get to break this into components, that our forces are vectors. These are 2-dimensional forces, and we're going to be dealing with 2-dimensional motion and acceleration. And we know that what's happening in x and what's happening in y both must be 0. Because these 2 dimensions are perpendicular to one another, they're independent. I can't have motion in x canceling motion in y. They're just completely independent, so you can break up this equation into these 2 separate equations. So what is the equilibrium model? And I want to highlight that this is going to be one of 2 models that we work with in forces. And the equilibrium model is just mechanical equilibrium, that we believe the situation that we have is a problem that can be modeled with equilibrium, meaning that net force is 0, acceleration is 0, change in velocity is 0. This can be an object either at rest or an object moving at constant velocity. So we're going to be modeling the object as a particle. That means we can draw it at a black dot and all of the forces act in the same location. We don't care where the forces are on our object. We can simplify it to a particle. Now, in both these situations, we have equilibrium, either a particle at rest or a particle moving in a straight line at a constant speed, meaning constant velocity. So in both of these cases, we have 0 acceleration. So Newton's second law says that your net force is equal to 0, and we can then break this up into x and y components. If it's 3 components, x, y, and z components. And when we draw a free body diagram, which we've talked about before, you would still draw every single one of your forces, but off to the side, you would label that your net force is 0. You don't need to label that your acceleration is 0, but in this case, it's trying to drive the point home. Now, the limitation in this case is very important. The limitation is that this is going to fail if the forces aren't balanced. What does it mean for forces to be balanced? Well, this just means that when you sum up your force vectors, you get 0. So balanced is a way of saying canceling out, but in this case, note that in this free body diagram, we have 3 forces, and so all 3 of them actually cancel out. That if you do your vector addition, you get 0 in this case. So how would we do this? To just verify quickly, I start with my force vector 1, and I want to add force vector 2 to it. Now what you have to do is then move force vector 2 to the tip, and then we say, okay, now I want to add force vector 3 to it. So again, I'm going to be able to move that. And I see that when I add force vector 3, that brings me back to the origin. So the vector sum of these 3 forces is equal to 0 because it's bringing me back to the origin. So if that doesn't happen, if you actually have non-zero net force, this F net doesn't equal 0, you can't use the equilibrium model. Now obviously that's going to happen plenty of the time. That's going to be covered in the next section of videos. So there's going to be many situations where you need to apply the equilibrium model, and part of the challenge, part of the physics, is identifying that you have an equilibrium situation. So we will now do some practice and thinking about how equilibrium relates to free body diagrams like I just showed.